All right, so it's just gone 1 o'clock, so we might make a start for today. So thanks everyone for coming, and we'll get a few more people coming in, I'm sure, as we go. So today we're joined by Matteo Contini, and Matteo is a researcher at the intersection of computer science and marine biology, and he's just recently completed his PhD. Congratulations, Matteo. He specialises in computer vision and deep learning for marine data, and his work focuses on creating standardised, reproducible workflows specifically aimed at quantifying ecological changes in tropical reef environments across multiple spatial scales. So I'm really excited to hear from Matteo. Thanks so much for joining us again, and please take it away.
Thank you very much for inviting me.
Let's make you feel welcome. Okay, now take it away.
Thank you very much. Thank you for inviting me, and thank you for being here. I'm Matteo Contini. As Scarlett said, I recently completed my PhD in November 2025, and the title of my PhD was Multi-Scale Mapping of Changes in Tropical Reef. It was a PhD jointly conducted between Inria lab in France within the PlantNet team and Ifremer lab in Reunion Island, a French island near Madagascar. And let's start with a small introduction. So these are two photos that I took in Reunion Island, the Saint-Lô Lagoon, one in December 2023 and the other one 1 year and a half later. We can see the degradation of Porites coral massive class. And this is not only an isolated case of Reunion Island, but during the last 30 years, we lost more than half of the total coral coverage in the world. So the research questions of my PhD were, can we actually map a coral reef in shallow waters with a large coverage, low cost associated to data collection and processing? We will now try to answer the first two questions. So traditional monitoring methods employ expert scientific divers that do transects underwaters. Probably most of you know underwater visual sensors. The big advantage of this kind of survey is the taxonomic accuracy that we can achieve by deploying expert divers that looks closely to corals underwater. But we have also three main disadvantages. The first one is the reproducibility, because there is an intrinsic bias in the human being, in the human that is performing the survey. The spatial coverage we can achieve with underwater visual sensors is limited, and the deployment cost of this kind of survey is really high. And there are also safety risks related to diving. So during last decades, new autonomous data collection tools have been developed, like autonomous underwater vehicles, autonomous surface vehicles, aerial drone, and satellite imagery. Of course, the resolution of the data we can collect underwater is higher than the resolution of aerial images collected by drone or satellites. But the advantage of aerial images is that is the spatial coverage. So as we move up into the sky with this kind of autonomous data collection tools, we can increase the spatial coverage, and often we decrease also the deployment cost of data collection. There is a big question now, how to treat this huge amount of data that we collect with the autonomous data collection tools. We will now try to answer this third question, how to process all this huge amount of data collected by autonomous platform in a low-cost manner. This is an image collected with an aerial drone in the Hermitage Lagoon in Reunion Island. And thanks to artificial intelligence technique, we can automatically predict which species are, or which classes are present on this image. For example, within the multi-label image classification setting, we will say on this image, we have corals, we have sea cucumbers, and the sand habitat class. The advantage of this kind of image or computer vision task is the low annotation cost. So annotating one image takes in average from our experience 30 seconds. And it's easy to train an artificial intelligence model performing multi-label image classification. The two main disadvantages are that we don't have a spatial detail about where the predicted classes are on the image, and we cannot detect individual objects. So we have a second task, the semantic segmentation. In semantic segmentation, we outline all the objects that are present on an image. So this time we know that we have 5 sea cucumbers present on the image, and not only the sea cucumbers class that is present. The big advantages now are that we have a pixel level information about where the classes are on the image, and this can enable object detection, spatial coverage computations, and so on. The huge disadvantage is the high annotation cost related to this task. Based from our experience, annotating an image takes an average 30 minutes. So there were already existing works on computer vision applied to imagery. For example, one of the most famous is the Allen Coral Atlas. The disadvantage of the Allen Coral Atlas is that performances are degraded in many reef areas, limiting the ecological relevance of these maps for local management and conservation applications. For example, these are the predictions made by the Allen Coral Atlas in Reunion Island. They predict the presence of corals everywhere. And from ground truth surveys, we know that this is completely false. And this is confirmed by a study published 2 years ago by André Fouet. There were other studies using aerial data collected by drones and underwater data collected by autonomous surface vehicles. They performed artificial intelligence predictions on aerial and underwater data. But the main disadvantage is that they do not take full advantage of the synergistic use of underwater and aerial data. So this motivated my PhD. In my PhD, we try to merge 3 different scales of data. We have fine scale data collected by citizens and with autonomous surface vehicles. And the objective is to try to pass the information from the fine scale to the medium scale, so that we have a teacher model, that is the underwater model, a student model, that is the aerial one, and we train the student model to replicate the performances of the teacher model. Once this upscaling process is done, we try to mimic the same approach and pass the information from the medium scale to the large scale to airborne collected data and satellite data. When I started my PhD, we didn't have data combining underwater and aerial data with a good geolocation. So we built a data set ourselves. And the main question was how to share all this data in an open science manner with the scientific community. We then ask ourselves, can we actually develop a reproducible and low-cost method for fine-scale coral reef monitoring? We then try to combine, as I said, underwater predictions and aerial images for extending the coverages of coral reef surveys. And then by mimicking this approach, we try to pass the information to larger aerial surveys. We now start with the first part of the presentation. I will present you Citizen Atlas, a collaborative data set of underwater and aerial marine imagery. So these are a few stats about the Citizen Atlas. We collected more than 2 million images, either by scuba diving, doing paddle, kite surf, thanks to a citizen science-based project, or using scientific platforms like autonomous surface vehicles or aerial drones. And these images have been collected all over the Indian Ocean during the last 10 years. And this is an example of a session of a data collection event published on Zenodo platform. So what is a session? A session is a data collection event that is performed in a fixed place, in a fixed date, with a fixed platform. So for example, this session has been performed in the Aldebaran Atoll in Seychelles with an autonomous surface vehicles in October 2022. And once we collect raw data, these raw data are enriched with metadata coming from the GPS, IMU sensors, or environmental variables. Then we filter useless imagery thanks to an AI model, and we can get 3 different types of outputs: bathymetric maps, photogrammetry models, or AI classification maps. Each data collection event has raw data and process data, and thanks to DOI versioning, we can describe raw data and process data under the same digital object identifier so that they are connected. And then, since each session has an assigned DOI, we can group all these sessions under the same record that we call the Citizen Atlas. Citizen Atlas brings together all the sessions that are publicly available, and thanks to a frozen version of the code that process our data, thanks to a frozen version of the data that is published on Zenodo, and thanks to an open source execution environment, we can say that we are making open science. And this is really important for us for reproducibility concerns, since Citizen Atlas is not totally fair. Fair does not mean reproducible, but we have a community on Zenodo so that people can contribute our dataset by maintaining authorship on their data and by using only our standards. We shared all the annotated images on Eigenface so that AI practitioners can load our dataset with 1 line of code. We have, of course, an organization on GitHub, and we published a dataset so that the whole workflow is described and people can contribute our dataset. We already had some contribution from Madagascar and Seychelles. And only a little stat: since its publication in 25 September 2024, the dataset has been downloaded more than 3,000 times. Let's now start with the second part of the presentation. I will talk to you about the fine scale model working on underwater images. So this is Plancha. Plancha is a low-cost autonomous surface vehicles that has been developed by a colleague of mine. These are 2 images showing Plancha. So it's a cheap bodyboard from Decathlon, and we mounted an eco sounder for bathymetric data collection. We have propellers for autonomous navigation, an action camera for vision data collection, and in the waterproof case on the top of Plancha, we have the batteries, the differential GPS, the autopilot, and all the electronics. And this is the workflow of Plancha from raw data collection to final data and metadata publication. During my PhD, I was in charge of integrating the camera to Plancha. It was not trivial at all, since, well, of course, we can collect video data, but since the camera is underwater, we cannot geolocate in a easy manner all the frames that we get from images. So we had to firstly correct the GPS position using real-time kinematic, post-process kinematics, or precise point positioning techniques. And then by taking into account the difference between GPS time and UTC time, attach the position computed by the GPS to the images collected by the camera. We attach other type of metadata to the EXIF metadata of the images, like roll, pitch, yaw, angles, bathymetric metadata, and so on. And these are the kind of output we can get at the end of a plancha session. So we have bathymetric maps. We have orthophotos that can be computed after performing structure from motion techniques on the collected imagery, if we have sufficient overlap between them. And we have some prediction maps. These prediction maps are computed for 31 different classes. These classes are coral morphotype classes taken from the Global Coral Reef Monitoring Network, a standard diffused in the Indian Ocean. We have algae classes, habitat classes, and custom classes that we added for the needs of our project. We annotated almost 15,000 images using the multi-label image classification technique. And one important thing is that this is the only subset of images that we annotated during the PhD. So no aerial images have been annotated at all. No images have been annotated using the semantic segmentation techniques. We took the most simple annotation task, the multi-label image classification, and then we annotated 14,000 images, and we stopped. We were, it was enough, and we performed the multi-label image classification. This is the distribution of annotated images among the 31 classes. And we trained an underwater computer vision model based on DynoV2. DynoV2 is a really famous family of transformer model. We only put a custom classification head on the top of it. And we trained DynoV2. This is a wordplay in French. We trained our DynoV2 model on the Citizen Atlas image dataset. And then we performed predictions on all the 2 million images we collected with autonomous surface vehicles. These are some examples of predictions. Here, you can see some underwater images collected in the Algebra atoll, geolocated on a GIS software. We can actually see that there are some massive corals, and these are the predictions made by the DynoV2 model. So the higher is the probability of presence of the no acropore massive coral class, the closer the color is to red. So it seems to work pretty well. And if we zoom out on 2 autonomous surface vehicle session, we can see that the coverage is still limited. So in our second part of my PhD, we wanted to extend the spatial coverage we achieved with our data collections event, and we started collecting data using an unmanned aerial vehicle, an aerial drone. But as I said before, we didn't want to annotate aerial images. So using the knowledge distillation technique, we tried to train a student model working on aerial images that have the task of mimicking the performances of a fine-scale model trained on the underwater images of the Dinovedo model. And since the predictions of the underwater model are geolocated up to the centimeter, we can actually pass the information from one scale to the other if we have overlapping data. I will start now the third part of the presentation from underwater to aerial. But in order to do it, I have to introduce the concept of photogrammetry that probably most of you may know, but I will explain it anyway. So what is photogrammetry is the process of creating accurate 3D models thanks to multiple overlapping images. So let's take, for example, this aerial image collected in the Hermitage Lagoon, showcasing some corals, sand, and sea cucumbers. This other image that is overlapping with the previous one on the x-axis. And now take these two images that are overlapping with the previous two images on the y-axis. Thanks to photogrammetry, we can actually build a 3D model and then split it in a 2D dimensional space in order to obtain this image that from now on we can call an orthophoto. If we zoom in on the orthophoto, we can actually see that we can distinguish corals. So here we can see that we have some corals. We can maybe guess the coral morphotype, even if it's difficult. And we can guess that there is some sand on the right. But distinguishing the coral species, for example, is pretty impossible. But imagine that we have the information about the corresponding underwater images. For example, in the red rectangle, imagine that we know that we have this underwater image. It would be much more simple to say, okay, we have a postiliopar coral in the middle, some branching acropora on the right, some digitate acropora on the left. And now the question was how to combine underwater and aerial images in order to pass the information from one scale to the other. We developed two different approaches. Unfortunately, I don't have time to show you the first one. I will talk only about the second one. And the second one aims to build a semantic segmentation model working on aerial data that is trained by multi-level predictions made by the underwater model. So here we have in the background an aerial orthophoto collected by an unmanned aerial vehicle. And each green point corresponds to an image that has been collected thanks to the autonomous surface vehicles. So we can pass all these images to the underwater teacher model, to Dinovedo, perform predictions for all the classes we study. For example, these are the predictions for the acropora branching coral class. Once again, the higher is the probability of presence of this class, the closer the color is to red. We can interpolate our predictions in order to obtain a continuous raster. And then we can use this raster along with the background aerial image to train a semantic segmentation model on the aerial scale. This is the complete workflow we used. So we have underwater images. We pass them to Dinovedo model. We perform multi-level image classification. Since images are geolocated, we can spatialize our predictions. We can rasterize and interpolate them to obtain continuous predictions. And then by coupling these predictions with aerial data, we can train an aerial student model in a weekly supervised semantic segmentation setting. We can get some predictions, and then we refine these predictions by passing the output mask to the segment anything model. We train a second time the student model, and finally we get our refined output. And these are the predictions we obtained, for example, on an aerial survey in the Hermitage Lagoon in Réunion Island. The big advantage now is that since we are in a semantic segmentation setting, we can actually compute coverages. We can count objects. And if we zoom in, we can actually appreciate how coral morphotypes are outlined, like massive coral class, tabular coral classes, even if we still have some misclassification errors that are outlined by black circles. This work has been presented last year at the joint workshop on marine vision at the ICCV conference, and has been the object of a publication some weeks ago. Let's now start with the fourth part of the presentation. So assessing the potential of upscaling from low to high altitude aerial imagery. So once again, by mimicking the approach I showed you before, we trained a student model on high altitude collected aerial imagery collected by airborne or satellite, using the predictions this time made by the low altitude aerial model trained on unmanned aerial vehicle images. These are two images representing the same zone. On the left, collected with an aerial drone, and on the right, collected by the IGN organization. IGN is the National Institute of Forestry and Geographic Information in France. And each 5 years, they collect imagery, aerial imagery all over the French territories, and they publish them in open source. We can see that the resolution of the image is not the same. On the left, we have 1 centimeter per pixel, so we can recognize coral morphotypes and even a small sea cucumber on the right. While on the image collected by the IGN organization, we cannot distinguish any coral. Even say that there are some corals is difficult. Distinguish the coral morphotype is impossible. So at the beginning, we were skeptic about training a model on images that had this kind of resolution, 20 centimeter per pixel. But we tried anyway. So we used the predictions made by the model working on aerial drone images to train a model on the airborne collected imagery. And these are the results. At the end, we were really surprised, since by using only 2 sessions of aerial drone imagery, we perform predictions all over the lagoon in Réunion Island. These once again allow us to compute coverages, and all the predictions are publicly shared on the citizen monitoring website. So here we can see how the model performs on IGN imagery. And once again, we can still recognize some massive coral morphotypes. And we did not expect this at all. The big advantage of working on satellite or airborne collected imagery is that we can compute macro changes without collecting ourselves data. So data are publicly available, and we can perform predictions. And here we have 2 different images of the same zone in the Hermitage Lagoon On the left, an image collected in 2017, on the right in 2022. And thanks to this kind of techniques, we can actually detect some macro changes events, like the advancing of sand tongue at the detriment of corals. This phenomenon has been detected also by Bajuk in a study they published in 2019, but they used hyperspectral and multispectral data. So since we obtained the same results by using RGB images, we are pretty satisfied. Let's now end the presentation with a discussion. So this is the outline of the methodology we built during my PhD. We shared all the data we collected in a FAIR++ way. We still have a contribution to the Citizen Atlas dataset. And this data can be used for training models, but also for performing predictions using your own model, or for ground truthing your models in the Indian Ocean. It's a collaborative data set, and our aim is that it can be used and can be useful for a lot of people, a lot of researchers and citizens. We developed a fine-scale underwater model that works in a multi-level image classification setting. Then by combining underwater predictions and aerial images, we upscaled the predictions, the fine-scale predictions to the medium scale by using two different approaches. I showed you the semantic segmentation approach, but the other one, I don't have the time to show you, trained an aerial student model in a multi-level image classification setting. So by using the same task of the teacher model, and then by mimicking the same idea, we pass the information from aerial drone data to airborne collected data. Of course, we have some limitations. The first is that data constrained to the Indian Ocean, in our case. A possible future direction would be to integrate the data coming from the global coral reef monitoring network that are available all over the world, in order to extend the predictions to other countries. And thanks to the standardized workflow we created, thanks to Citizen Atlas, we could actually imagine a citizen performing kayak surf sessions, or simply scuba diving, collecting data, sharing them thanks to the Citizen Atlas web platform. And then we can integrate this new data in our model, train it, and perform predictions in different countries. And a second, less trivial way to overcome this limit is to train multimodal models. So the integration of environmental and biological metadata would, of course, have the model to recognize site-specific classes. We could actually imagine a model working not only using images, but eDNA data, acoustic data, environmental variables, or hyperspectral images. Taking advantage of all these informations in order to predict coral distributions all over the world. And second huge limitation of the upscaling method I just presented is that in the fine scale setting, we had 31 classes in a multi-level image classification setting. And then when we upscaled to aerial images, we were able to keep only 12 classes in a multi-level image classification setting and the 5 classes in a semantic segmentation setting. So we have a huge loss in the number of classes we can actually detect. And by passing to the airborne satellite scale, we kept only 4 classes. So this is a limitation that is inherent to the resolution of the images we use, but also to the number of images we annotated at the fine scale level. So a trivial way to overcome this limitation is to collect more data, annotate more data at the fine scale. And of course, this will help the model when upscaling to keep a higher number of classes. And a less trivial way would be to use underwater photogrammetry. At the beginning of my PhD, this was the actual objective. We aimed to build underwater orthophotos, like the one you see on the top of the screen, by annotating this orthophoto in a semantic segmentation setting, train an underwater model, and then passing the information from one scale to the other. Unfortunately, we were able to build this kind of orthophotos only 2 years after the beginning of my PhD. So I had to change my mind, and I moved to the multi-level image classification technique I just showed you. But this is still a very interesting path to follow, since the precise mask that we can build thanks to semantic segmentation would help the model to retain a higher number of classes when upscaling from underwater to aerial data. And another problem when I started my PhD was that no open source available datasets exist 3 years ago. So we had to annotate ourselves underwater orthophotos, and this is really time consuming. But during the last year, 2 different datasets, like the Coralscape dataset published by Jonathan Souther, has been published. So we could actually imagine to train a model using their data and to fine-tune on a small annotated data set of ourselves, build our semantic segmentation underwater model, and then performing the upscaling process we just saw. And I think it's all. Thank you very much for your attention. And I'm actually searching for a postdoc in the Western Australia. So if you have any suggestion, they are welcome. Thank you very much.
Thanks so much for that talk, Matteo. That was fantastic. Do we have any questions in the room for Matteo? Anybody? I've got one. I want to ask about the kite surfing data that you mentioned. So you had a surface vehicle and also some citizen scientists. How high quality was that data? I'm imagining if it's like a kite surf that it's, you know, not super clear images, maybe motion blur or, yeah, I can't imagine that. Can you explain that a little bit more?
Yeah. Okay, so we had citizen size collected data with paddleboards, mask or kite surfing. As you say, the kite surfing collected data are the most difficult to analyze since images are really blur. But the big advantage, we annotated them so we can, if we can distinguish seagrasses, habitats, coral morphotypes, sometimes is impossible, but sometimes we can distinguish branching corals. If we can do it, the model can do it. And the advantage of merging citizen size collected data with high quality data collected with the autonomous surface vehicles is that the model can learn to generalize to this different type of data. So we have different point of views We have kite surfing data collected a little bit from the side, but from the surface. We have paddleboard data that are collected like autonomous surface vehicles from a top view at the surface, data collected with by scuba diving that are collected by the side. So once the model, at the beginning, the model, when we don't have so much annotated images, the model understands nothing. So you say, okay, this is an acropore branching coral. We see it from the side. On this other image, we see from the top. And he's not able to recognize, to learn that it's the same class. But once you annotate some hundreds of images, this diversity in the data collection platforms allow the model to generalize to new type of images. And this is actually a huge advantage of our data set. And I don't know if I answered your question.
Yes, you did. Thank you, Matteo. Does anyone online have any questions? Oh, there's one in the room. Mick, do you want to go?
I was just wondering, because you made the citizen science data set, and you said you want to open it up. Like, is it free, or like how are you hosting such? Because like I guess some of the data sets we collect are like 10,000 images in one mission. Is that kind of your goal, to be able to host like levels of annotated data at that scale, or is it just small for now, I suppose? Or I don't know if that's an obvious question, but does it make sense?
Yeah, are you asking if all the annotated images and all the data we collected are openly available, are free, and shared on web platforms?
Or as in, are you, because you said you wanted to open it up to have like a global amount of data. I was just wondering if like people could submit data to you as such, like so it was available on that website.
Yeah. People can actually contribute to our data set. All the data we have are already open. They are shared on Zenodo. And people, if they want to contribute to our data set, they have only to respect the standardized naming convention we used. And then we can give them access to our organization on Zenodo, and they can contribute to our data set, and their data will be automatically shown on the web platform and integrated so that people can filter data based on time criterion or locations or data collection platform, and they can download them. We already have some thousands of images that have been shared by Madagascar institution, and they had only to use the same naming conventions. So at the beginning, it's a bit annoying. You have to put all the images in a DCIM folder. You have to put all the annotation in an annotation folder and things like that. But once this is done, we have open source codes that automatically process your data and publish them in open source platforms.
Awesome, thank you. Anyone else in the room? Beverly? I don't think that one's working, so.
Thanks very much for the talk. I don't have a marine ecology background, but I was wondering what the process is like to annotate your own data set. Like what kind of software is used, anything like that.
Okay, thank you very much for this question. I don't have neither a marine ecologist background, so fortunately, I was not implied in the annotation process. But for the multi-label image classification annotation process, it's pretty simple. We build our own software for annotating images, but it's trivial. It's more complicated when you want to annotate semantic segmentation images. And when I started my PhD 3 years ago, no segment anything model or ChatGPT models were available. So semantic segmentation annotations were performed using CVAT tools, for example, but it was painful since you have to make outline each object manually on the image. Now you have a semantic segmentation model like SAM that are already integrated in annotation software, so that you can only click on an object, for example, on a coral in an image, and the model will segment itself the object on the image, and you have only to assign a label. So this is much more easier. And I think people that annotated images now, most of them use this kind of speed up models to perform at least the mask, and then they have to assign themselves the class they are studying. And for what concerns the assignment of the label to different masks, in our case, since we are working on coral morphotypes and not on coral species, it's much more easier. So coral morphotypes are really different between them. So it's easy to distinguish a branching acropore with respect to a tabular acropore. When you're working with coral species, is much more difficult. And I think that the process needs some expert marine biologist. But fortunately, this was not our case.
We have just one question online, and the question is, what do you think is the biggest blocker for fully leveraging citizen science data? Is it better low-cost hardware? Is it more precise geolocalization? Is it more accessible knowledge on how the data should be acquired?
I think it depends on your goal, since if you want to perform, I don't know, for example, to assess the health of corals in a specific site, if you want to detect bleaching events or some huge scale events like this, you can use citizen science data, even if the quality is not perfect, even if the geolocation of your data is not perfect. You will, of course, have some errors, but the fact that you can collect the data at a huge scale and by free, it's a huge advantage. And if you want to detect these macro events, I think the only bottleneck, the only problem is that you have to get some sensibilization to the citizens. You have to say them, you need to collect data, it's useful, and if you share your data with us, we all have some benefits, since the habitat will be kind of better protected. But if you want to perform some really specific study, like in our case, I don't know, if you want to distinguish coral morphotypes, if you want to pass the information from one scale to the other, and you need really precisely geolocated data up to the centimeter, you have to train citizens, you have to form them, and you need time in order to do it. You need people. And maybe this, in the second case, this is the huge bottleneck, the availability of people that can train, that can accompany citizens to allow them to collect useful data for you.
Awesome. Well, thank you so much, Matteo. Thanks everyone for coming here today. And can you join me in thanking him one more time?